All right, so the IHD is, again, the index of hydrogen deficiency. And what it tells me is number of pi bonds, or the number of rings. Right, so if I have an IHD of 2, that means I can have 2 rings, 2 pi bonds, or a combination of 1 and 1, right? So anytime you're doing NMR and you're dealing with a structure, you want to calculate the IHD for the molecular formula. So the way you calculate it is HREF So it's HREF minus H molecule over 2. HREF is going to be 2N plus 2, where N is the number of carbons. Right, so whatever the number of carbons are in that molecular formula, you just stick it into that formula, 2N plus 2, that'll give you HREF. And then H molecule is whatever's in the formula. Like, so for this one, I think we calculated the IHD to be 0, right? Because HREF was 2N plus 2 right here. 2 times 4 plus 2 is 10. And then you have 10 hydrogens here already. So you stick that in for H molecule, 10 minus 10 is 0. So that means that there are no rings and no double bonds for this structure. So actually,
so where did you get the 2 times 4? Like,
say that again.
Like, where'd you get that from?
So HREF is what we call a reference compound. So for any organic molecule, right, the formula is C. So CNH. So it'll write a little bit better. So CNH 2N plus 2. That's the formula for any given organic compound. Right. So I just take this part from that, the 2N plus 2. That's HREF. So for any organic compound, under normal circumstances, the molecular formula is going to be CnH2n plus 2. Right. That's from that's something that, well, I don't know if I know I discussed it with my part 1 class. I don't know if Abdallah talked about it, but that's just the basic molecular formula for alkane. So you use that as your reference compound. So that's what that little term HREF means. All right. Does that make more sense now?
Yeah.
All right. So let's look at this molecule and see if we can pick out what's what. I'm going to erase this because I saved it. Let's see. All right. All right. So you can look at the spectrum and see that you got 4 signals. And then one of the signals is integrating for 6 protons. One is integrating for 1 proton. And then this is the OH. Right, remember I said the OH, sometimes you can see it, sometimes you can't. Excuse me. So that's the OH proton, and then you have a signal here, a doublet, that's integrating for 2 protons. All right, so let's see if we can figure out what's what. So for the doublet at 1, right, for the doublet at 1, what do you think? Look at the integration and tell me what you think that signal is, what set of protons that signal represents. Right, notice it's integrating for 6 protons. And there'll never be a carbon with 6 hydrogens on it. And so it must be representative of more than one carbon or more than one set of protons. So which ones do you think?
Would it be that them 2 hydrogens, the one that's highlighted pink?
And pink? Okay, so.
I mean, no. I mean the one that's highlighted purple. That's what I mean. Because then that would be 3, then the pink one will be 2, and it'll be 5 plus 1 is 6.
No, you're thinking, you confusing the integration with the splitting pattern. See, the signal is a doublet. But the number of hydrogens that it represents is 6 hydrogens, but the actual signal is split into a doublet. So the splitting pattern and the integration are different. That's 2 totally different concepts. So which one of these? What about the blue ones? Are they equivalent? The 2 CH3s that are on that like isopropyl type motif right here?
Yeah.
I would say, yeah, they're equivalent.
Yeah, they are.
Yeah. And that's a total of how many protons? It's a total of 6 protons, is that right?
Mm-hmm.
So why would it be a doublet? Let's think about that. So right here, there's a hydrogen there, right? And so that CH3 is going to split with that. If we do the N+1 rule for that CH3, N equals 1, and then N+1 is going to be 2. So that's going to be a doublet. Is that right? Because you're looking at these hydrogens, and on the carbon next door to those hydrogens, right here, there's 1 hydrogen. Anybody not see that or disagree with it?
Okay, so when it comes to splitting, right, it only counts that 1 hydrogen. Like,
Yeah.
I always get confused. It doesn't count anything else. It's just that 1 extra hydrogen.
I erased that. Should have kept it. If I got two carbons next door to one another, the only thing that matters is for this hydrogen is what's over here on the carbon next door. So when you're looking at the splitting pattern or the multiplicity, you're looking at what the carbon, where the proton is that you're looking at. You're looking at what's adjacent to it. Right, so for that CH3 on the carbon next door, that's 1 neighbor, 1 hydrogen. Right, so when you apply the N+1 rule, you just, if N is 1, stick the number in, and you get a doublet. Right, you only count what's adjacent. All right. And then since the hydrogens are equivalent on both CH3s, right, you're not going to get 2 doublets. You're going to get 1 signal, but the intensity is going to be increased because it's representative of 6 hydrogens, right? Look at that doublet, the size of that doublet relative to the rest of the signals. Do you see how much higher it is than the other signals? That's because the intensity increases because it's representing more hydrogens. All right, so the OH, we'll skip that because it doesn't couple. Remember I said that before, the OH doesn't split. All right, what about the CH2 that's adjacent to the OH? What signal do you think that is? You only got 2 signals left to choose from, right? So that CH2 is not going to split with the OH. So the hydrogen that's on oxygen is not considered a neighbor, right? So how many neighbors does this set of protons have right here? The ones I just highlighted in green. One neighbor. That's exactly right. So for that set, N is going to be 1, and then N plus 1 will be 2. So that should also be a doublet, right? And if you look at the location, is it upfield or downfield relative to the other signals?
Down.
It's downfield.
So do you not count the CH3?
They're too far away.
Okay. Then where did you get 1 from? You still count that 1 hydrogen.
Right. On the carbon next door. If it's not next door, it won't split. Let me see if I can illustrate it. Let's say I got a carbon, a 3-carbon, a 4-carbon chain, right? And it's just got a bunch of different functional groups. And then you got hydrogens here, 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 and then here. So all of these are different. That's why I put different letters, R, X, Y, B, A, whatever, right? This carbon right here is not going to split with those hydrogens are not going to split with these all the way down here, right? The splitting takes place when this proton experiences the magnetic field of the proton next door to it only. So right here, that's the only hydrogen it's going to split with. It can't split with anything further than 1 carbon away.
Okay.
Yeah, so I'm not going to count. I'm not worried about the CH3s. All I'm looking at for this set of hydrogens right here is what's on the carbon next door, which immediately next door, which is that carbon right there. Anything else is too far away. Right? So that's why it's only showing up as a doublet.
Oh my God, why my face is sticky? Can't my do back to come down? That shit was blowing me.
Right? That's why it's only showing up as a doublet. All right. Why is it so far downfield?
Because it's right next to that OH, right?
Because it's next to oxygen. Exactly. Right. So the last signal is here, right? And it's a multiplet, which means it's split into multiple lines. And let's count them up. We got, so 1, these little shoulders out here count. So it's 9 lines. So N plus 1 will be 9 for that signal. The only proton that's left is this one. Right here. So how is that signal split into 9 lines? That's the question. What is that proton splitting with? Right? You see the carbon that it's attached to right here. And that carbon is bonded to this carbon right? This one and this one. And every one of those carbons has hydrogens attached to them. So that's why you see that split up into that multiplet. Because it's got 8 neighbors, right? 3, 3, and 2. Are y'all following that or no?
Mm-hmm.
Yeah, so it's got 8 neighbors, so it's going to be split into 9 lines. That's why you see that multiplet. All right, any questions about that?
So when you have OH and because I remember in the video you had like OH and NH2,
Mm-hmm.
they just come up as one singlet, like
Yeah, they don't split.
Okay.
Yeah, they don't split with neighboring protons. They only show up. Sometimes the OH, this is really generous to the OH proton because most of the times if you take an NMR, the OH proton is going to look something like this. It's just going to be a bump. It's not going to be resolved like a real sharp singlet like that. It'll be a bump somewhere. Sometimes you can't even see it. So, but again, it depends on who made the example. Like I didn't write this question. I took it from somewhere else. So sometimes people will show it. Sometimes they won't. It just depends. That's why when we first started and we went through and picked out the protons and how many signals this thing would give, we said 3 or 4, right? Because the 4th one would be the OH, whether it showed up or not. All right, we only got one more structure up here to deal with, and that would be this one. We said 8 signals, so we're about to find out if we were right. So let's go to the last spectrum. Oh, real quick, let me also talk about this infrared. I talked about it Monday, but I'm gonna just rehash it. So this is the infrared that's shown here. I'm gonna erase these. Right, so again, if you got an alcohol like this, there's a really distinctive stretch in the infrared that's always going to show up, and it's right here. It's this bumpy looking stretch right here. That's your alcohol stretch, your OH stretch. I have it written right here. That's your OH stretch. That if you got an alcohol present, that's always going to be there, and it's always going to be somewhere between 3,200 and 3,400 reciprocal centimeters. Always. And it always looks like that. It's what you call a broad stretch. Right. So that's one of the infrared stretches that you should memorize. Right. The same with the alkyl stretching. All of this crappy looking jagged mess right here. That's for all those carbon and carbon hydrogen single bonds. Right, that stretch is ubiquitous. It's always somewhere between about 2,800 and 3,000, and it always looks the same, jagged and rough like that. Right, and there's one other stretch in this infrared that's important, and that's right here. That's that C. It's a carbon oxygen single bond stretch, and it's usually somewhere between 1,000 and 1,150 reciprocal centimeters. Right, so that's 3 major stretches that you should probably commit to memory. The alcohol stretch, the alkyl stretch, as well as the CO single bond stretch. I think in that infrared video I sent you, I pointed all those out too. All right, let's go to that last question. Now point out a couple of the stretches here as well. Let me paste this down here. All right. So how many signals are in that spectrum? Not splitting patterns. How many signals do you see?
5. Wait.
5 signals. All right.
4. Wait. 1, 2.
Just 6 signals. Because this is one right here. Right. 7 signals, actually.
Mm.
All right. What does that mean when you got 7 signals in the NMR? What does that tell you about the molecule you're dealing with?
That is going to be a ring?
Mm-mm. You got 7 signals. What does that tell you about the number of non-equivalent hydrogens? How many different types of hydrogens do you have if you got 7 signals in your NMR? Shouldn't the number of signals be equal to the number of non-equivalent proton types?
Mm-hmm.
Yes. Don't be scared to say yes. The number of signals tells you how many different types of protons you have. If you got 8 signals, then that means you got 8 different types of protons in a given molecule. If you got 10 signals, it means you got 10 different types. If you got, let me go back up to here. Remember this last example that we just did, right? How many signals were in this NMR? 4 signals, yes? Oh, it's frozen, hold up. Come on. Sorry. Let me reshare it. Stupid technology. I think it's my Wi-Fi. They keep digging in the neighborhood. They land fiber optics, and I think sometimes they interrupt the existing stuff that's already here. Right? We said right here we got 4 signals in this NMR. So that means that in the compound itself, it's 4 different types of hydrogens. You had this set, that's 2. The OH showed up. So that made 3, and then the 2 CH3s are equivalent. That's 4. And the number of signals is going to tell you how many different types of hydrogens you're dealing with in a given molecule. Right? The number of signals tells you how many non-equivalent protons are present. The integration tells you how many of each are present. The location tells you where they are. And the splitting pattern tells you what they're connected to, right? Those are the 4 main takeaways from any NMR spectrum, right? The connectivity, the chemical environment, the number, and the non-equivalence. That's what you're looking for. So if you look at this molecule, we got 7 signals, right? We can pick them out. Everything on this chain is non-equivalent. None of those hydrogens are equivalent to each other now. All right. And then on the ring, obviously you got 3 different protons on that ring. So if you look at let me draw the hydrogens in on the ring, and then maybe it'll make more sense, maybe. So you got these 2 hydrogens here. And then these 2 here, right? And then on the chain, I'm gonna use a different color. You got CH2 here, CH2 here, and then here. And they're all different. And they all gonna show up at different places, right? So the number of signals, you can look at the molecule and see that's gonna give a signal, these will give a signal, this will give a signal, these will give a signal, and then 2 of the 3 on the ring are equivalent. We're gonna come back to that. about the ring part. And then the other two are non-equivalent. That's why you see one signal and then two more signals. So let's go down here and see if we can pick these out. Let's start at that triplet down here. What do you think? The integration is 3. So that signal represents 3 hydrogens, right? And if it's a signal that represents 3, and those 3 hydrogens are on the same atom, you can't pick one from each atom and say, oh, it's these 3. It's always going to be from the same atom. So which set of protons do you think that triplet represents?
Would it be the CH3?
That's the only atom there that has 3 hydrogens on it. So yes, it's the CH3. And then why is it a triplet?
Because it's next door to those 2.
Next door to a CH2.
Mm-hmm.
Right. So here, for this set of protons, N is 2, N plus 1 is 3. So it's a triplet. Right? We're going to label them. I'm going to call it A. So that's signal A. All right, let's go to the next one. Now, let me zoom in so you can count the lines. Right, so if you look at this signal right here, you got 1, 2, 3, 4, 5, 6 lines. If that signal is split into 6 lines, what does that mean as far as what's connected to it? How many neighbors should it have?
Yeah, it has 5 neighbors.
5 neighbors, right? Good. N equals 5. So N plus 1 equals 6. Now let's go back up to the structure. Which set of protons has 5 neighbors? That's the question now, because we can match it. All we need to do is which one?
The one next to CH3.
This one. That's good. Right here. Is that right?
Mm-hmm.
You got 3 on one side, 2 on the other side. So here, N is 5, and then N plus 1 is 6. Right? So that we're going to call B. Right? All right, now let's look at the next signal. How many lines is that split into? Let me zoom so you can count them. Right? It's 1, 2, 3, 4, 5 lines. You follow me? So what's the number of neighbors for that
4.
set of protons? How many protons are going to be around it? If it's 5 lines.
4.
4, right? So for that signal, N is going to be 4. N plus 1 is 5. So let's go and look. Which one of these sets of protons has 4 neighbors on the chain now?
The 2 hydrogens in the middle?
The 2 in the middle, right? Right here. So we're going to call this C, right? And N for C, N plus 1 is 5, because it's got 2 neighbors. It's got neighboring protons on this side and on this side. All right, so that's the signal for that. And then if you look at the one, and look at the integration, right? All of the integrations are showing up as 2 protons. So for this, you need some other clue to figure out what's what, because if they're all integrating for 2, you could say, well, I don't know which one it is, because all of those CH2s on the chain look the same to me. That's why you need to understand about the multiplicity as well as the location. Let's look at the last one. Obviously, it's this one, right? Because it's a triplet. So we'll call it D. This was C, that's D. Following?
Mm-hmm.
Now, why is it so far downfield compared to the other 3 signals?
Because it's next to that ring.
Next to the ring. And the carbon in the ring is sp2 hybridized. So that's just like putting it next door to a carbonyl. Even though a carbonyl would probably have a little bit more influence, the sp2 carbon is still a sp2 carbon. And so it's still going to de-shield that set of protons just a little bit, right? So the location, the connectivity, right? The number of hydrogens and the non-equivalence. Those are the 4 things we take away from any given NMR spectrum. Now, granted, some NMR spectra can be very complicated. Don't lose that. But I'm trying to keep it to where you can understand it, because you can have some really, really complex NMR spectra that, you know, it takes more than 30 seconds to interpret. Trust me. But for now, I think that's what we're going to take away from this. All right, let's look at the ring. One point to make about that ring, well, 2 points. Number one, look at where the protons show up on the ring, right? Remember, we talked about that. These are aromatic protons, right? They're aromatic protons, right? And so for the aromatic protons, they always show up somewhere between about 7 and about 8.5 or 9. That's the range. Right, for aromatic protons. The problem on those aromatic rings is it gets really weird when you talk about the splitting patterns and being able to tell them apart. It can get really convoluted, right? Because aromatic rings, you know, you can have like rotation. So you got rotation around this carbon-carbon single bond and all these other things that you can encounter when you're dealing with aromatics. All right, but what we do know is that at least 2 of those protons on that ring are equivalent, right? And then the other 2 are non-equivalent. So I'm going to go for these. I'm going to say that these 2 are the ones that's going to give those 2 other signals, right? And then the 2 up top next to nitrogen, I'm going to say that those are your equivalent protons. Right, so those 2 are going to give this signal right here. And then the other 2 protons will be here and here.
So when it comes to that bracket, it's just saying in total it's 4 hydrogens. They may be different.
Exactly. Exactly.
Okay.
That's exactly right. So the integration for this whole section is 4 protons, right? You can look on the ring and see you got 4 protons on the ring. All right. Any questions so far? Yeah. Well, y'all not that quiet today. That's good. It's Winning Wednesday.
I have a question. Okay. Mm-hmm. So in the practice video, you had said on the ring that the 2 hydrogens on the side mm-hmm. were different because they were attached to that that pi bond. So how come now you're saying that? Wait, you did say they were different. Never mind. Okay, it's the highlight colors. They both look pink to me for a second.
That's all right. All right, let's go to the next. Let me hit this infrared right quick. So for this structure, the infrared is really only going to give us a couple of things that we care about. The aromatic stretching, which is right here, right? That's aromatic stretching. It's usually pretty weak. And it usually shows up somewhere around 32 to 3,500. Reciprocal centimeters, right? And then what is this right here? What do you think? What's that signal? What functional group does that signal represent? Can you see the numbers? It starts at 2880, ends about 3000. It's jagged, it's ugly looking. What do you think?
It's that halide?
There's no halogens on the structure, but there's a big carbon chain, right? That's alkyl stretching.
So it's just alkyl, not alkyl halide?
Just the alkyl. Carbon, carbon, and carbon hydrogen single bonds.
Okay.
And it's always in the same, well, relatively in the same place. And it always looks the same. It's always jagged, like, and really rough looking. All right, let's do, much time? Oh yeah, we got time. All right, let's take this example right here. So we're gonna pick the products and then we're gonna match the products up with the NMR spectrum. All right. So if you look at this reaction sequence, the first reaction is oxymercuration. Second reaction is conversion of an alcohol to an alkyl halide, and then the third reaction is an organometallic reaction. It's a Gilman reaction. So what's the product from the first reaction? You got three choices. I didn't even make you have to draw it. I need some Jeopardy music playing. No takers. All the time you spend in part one. Got that nice B, A out of part one. What a shame. And we did this earlier too. We did it when we did the pre-existing stereo centers too. I'm not gonna go over it, but I'm gonna, for the sake of time, we're gonna pick the right answer. So oxymercuration is a way to make alcohols from alkenes. Right? See, we started with an alkene. It's Markovnikov addition of water, basically, across the double bond. Right? So the first reaction is gonna give me B. And notice where the alcohol is on the internal carbon, not the terminal one, because there's Markovnikov addition of OH and H across the double bond. All right. Now, what's the second product? Now, we did this semester.
C.
Come on with it. Who was that?
Quenisha.
So, virtual high five to you. Second product is alkyl halide, right? That's what thionyl SOCl2 does. It takes alcohols and turns them into alkyl halides, particularly secondary and primary alcohols. All right. What about the third reaction? We only got one answer left. Come on, somebody just say it proudly, like you already figured it out.
Oh my God, it's A. Oh my God.
Why oh my God? What?
You said proudly. I was excited.
Oh, okay, yeah. There you go. It's A, right? What is that? What does the Gilman do? You got a cuprate, or organometallic, and you reacting it with an alkyl halide. What is it going to do? Isn't that like we learned earlier, Cm plus Rx. Is that right? Then we learned that at some point?
Mm-hmm.
Okay. Just making sure I've been doing my job. I don't want to be getting a check for nothing. But we did that before, right? So the halogen is, well, the alkyl halide is Rx, right? And let me explain too. So the first reaction gave you the alcohol. It's the alcohol that gets reacted on by the second reaction, thionyl chloride. All right, and then what you get from that gets reacted on by the third reaction. Is that clear?
Yes.
Yeah, because the alkene, once you do the first reaction, the alkene is done. There's no more alkene. The star material for the second reaction is the alcohol. And then the star material for the third reaction is the alkyl halide. Does that make sense?
Yes.
All right. So we got our three products. And now we're gonna go down here to these NMRs and see if we can pick out what's what. Right. And I included the star material. So let's look at it. So we got infrared data, 3,000, and one of these stretches I didn't give you, but I'm gonna help you with this one. So you got 3,000, 2980, and then 1760. So the 1760, a lot of times, one of the reasons you can't use infrared as the definitive method for determining a structure is because sometimes you have functional groups that overlap, right? So the 1760, that's your alkene stretch. And sometimes it'll overlap with the carbonyl stretch. So what do you think? If you got an alkene stretch in the infrared, what do you think? Which compound is it? Which compound out of A through D contains a double bond or alkene?
I would
D.
think it's D.
D, right? Well, I think the speakers are messed up. That's what it is. Gotta be.
Yeah, they delayed.
No, they're not. No, they're not. I'm just trying to give y'all the benefit. I know it's homecoming week though. Even though there's nothing going on, it's mental. Like, God, leave me. I gotta sit in this class.
No, personally, I feel like this part is kind of more difficult.
Recently. I said that the NMR was a beast though. I did preface the whole section by saying it was a beast.
Because we started off slow, but then you start adding, and then
yeah,
I'm trying to keep up.
Though.
I'm trying to keep up.
Yeah, you gotta add. It's just like working out. You can't lift 5-pound weights and think you're gonna get big. You lift 5, get your form right, then you go to 10, then you go to 15.
True, but chemistry is like 5 to 25. You don't even get.
I took y'all 5 to 20. Now we on some 15s. All right, so let's draw that out. Let me draw that out. But you gotta say though, at least I'm not just throwing you to the wolves, and just I ain't gonna leave you floundering. At least I don't think I am. I think I'm pretty supportive.
It's not you.
Okay.
It's chemistry.
Don't be afraid of chemistry. It can't hurt you. It can only help you. All right, so here we go. So now that's my alkene, and we're gonna figure out how many signals we should see. Let's do that first. I always want to do that first. And I'm drawing these out on purpose. All right. So how many signals should we generate from this? And before you say a number, don't count the signals in NMR. Don't cheat, even though somebody already cheated. But it's okay. How many signals should we see? Is there any equivalence here?
No.
No, nothing is equivalent. So that means every one of these sets of protons should have its own signal. Everybody agree with that?
Mm-hmm.
All right. So with the alkene, we're going to skip that. We're going to come to that last because there's some information in there that I want to talk about. But keep in mind for that alkene, all three of those protons are different. How do we test that to see what's equivalent and what's not equivalent? Anybody remember? There's a test that we talked about doing for equivalence.
Is that by replacing one of the hydrogens with something else?
Speak up. You're right.
Oh, okay.
Go ahead. Whoever that was. Who was that?
It was.
I think she accidentally just left.
Oh boy. All right, but she was right though. She was right. You take a hydrogen off and put another atom in its place. Like if I wanted to compare these two, I swap each one of them out with a chlorine or bromine. Come on, Wi-Fi.
And that's when you get the diastereomers.
No, that's different. That's when you have a chiral center.
Oh wait, yes, by next to the chiral center. You're right.
Yeah. See, you know some stuff.
It's a lot. It's a lot to it's like 50 steps to one question.
It's a lot. I won't deny that. I won't lie to you and say, no, this is easy. It's not easy. That's why we're in the mess we're in right now with this virus. Somebody said, no, it's nothing. Nah, it ain't nothing, bro. But if you wanted to compare the two circled in red, right, you just pluck one off and put another atom there, and then you pluck the other one off, and then you compare the two structures. And you'll get two totally different isomers. So that's how you know that they're non-equivalent. And the same with the one that's pointed down. All right, so we should see 1, 2, 3, 4, 5, 6 signals, at least, right? So let's look at the ones on the chain first, right? So let's look at the CH3. Which signal out of these three signals down here do you think is the CH3? And why? How would you pick it out? Right, the location, you know, if it's an alkyl set of protons, it's gonna be somewhere between 0 and 1.5, somewhere like that. So location wise, it's fine, but what could you use specifically to pick it out?
It's neighbors, right?
Yeah, the connectivity. If you look at the signal, it's a triplet. It looks kind of bad on this. Oh, there we go. It's better now. It's a triplet, isn't it?
Mm-hmm.
So what does that mean? That means that set of protons, the carbon that those protons on, is connected to a carbon with two protons on it. Is that right?
Mm-hmm.
N is 2, right? Because it's a triplet. So N plus 1 is 3. Let's go back to the structure. Do we have, and then I didn't put the integration, but we're gonna go back and retroactively do it after we pick out the signals. So which one of these up here would be a triplet on the chain? Now, we're not looking at the double bond yet.
Wait, what do you mean? Oh, on the
chain.
Which will be a triplet?
Mm-hmm. Which one of them has 2 signals?
I don't know. Wait, triplet without adding a 1 or with adding a 1?
Well, you got to add the 1 for it to be a triplet because the signal is already known. It's already 3 lines. So the 1 is understood. So it means that carbon is connected to a carbon with 2 protons on it. So it's got to be the CH3.
Oh, we're still on that. I thought we finished that. That's why I was like, wait, okay.
See, now you're trying to go to the 50s. I'm trying to keep you at the 25. You're trying to go to the 100s. All right, so it's that one. Is that right? Let's label it. Let's call it A. Anybody disagree that should be a triplet and the location is okay? All right, look at the next set. Right here, I'm gonna change the color up. What should that signal be split into? How many lines? Look at the number of neighbors. Tell me how many lines it should be split into.
6.
6 lines, good, excellent. So for that signal, for that set of protons, N is 5. So N plus 1 is going to be 6. Let's zoom in on our signals down here. We got 2 signals to pick from. Which one is split into 6 lines?
One right next to.
One at about 1.4.
Mm-hmm.
Got 6 lines in there, so that means that N is 5. We already showed that. So we're going to call that B. It's the green set right here, B. Come on, man. All right. Now the other set of protons down here is foregone conclusion, right? It's got to be these, because we already picked out the other 2. We'll call it C. Well, how many neighbors does that have?
3.
3. Good.
Mm-hmm.
1 here on the alkene, and then 1 next door, a CH2 next door. So for that one, N is 3. So N plus 1 should be 4, right?
Mm-hmm.
So we're going to call that C. And it should be a quartet, and it is. 1, 2, 3, 4 lines. Yes or no? Now the alkene protons are kind of weird because, didn't mean to do that. Got my eraser too big. The alkene protons are kind of weird, splitting wise, right? But they do split. So for this one, let me give it a different color. I got 5 minutes. What should the splitting pattern for that one be? Right, it's got 2 neighbors on the left, right? And it's got 2 neighbors on the right. Is that right?
Mm-hmm.
But the fact that it's in an alkene, it's going to split with each one of those neighbors differently.
Mm-hmm.
Right? So it's going to split with that H, and then it's going to split with this H separately, in addition to splitting with the CH2. So that's going to give you a complex pattern. Right? That's going to get, so probably that H is going to be buried up in here. Can you see all of that?
So with splitting, complex splitting, when it does that, it basically, I don't know, counts as neighbors separately?
Yes. Yes. So it's going to split with the CH2 on the right, and then it's going to split with each of the hydrogens on the left. So what you're going to end up getting is a complex signal, a complex splitting pattern, right? So it's going to be like let me see. I think it's M plus 1 times N plus 1. This is 3 and 3. It's going to be something like 9 lines or something like that. But suffice it to say, it's going to be buried under here. So this is actually more than 1 signal, right? That's 2 signals kind of on top of each other. And you're going to get that for this proton, the one I have circled in purple. And then the other proton that's laid on top of it is probably going to be this one. But that one will be different, right? That's just going to be a doublet of doublets, right? Because it's going to split here and it's going to split here. So that should be a doublet of doublets, right? And if we look at the signal, you can kind of see that up in here. Right, those 4 lines, that's going to be your doublet of doublets. And then the other signal is going to be just difficult to pull out because of the overlap. All right. we got to stop there. We're gonna talk more about that on Friday.
Yeah, please.
For those of you who are here, remember, you might, well, who came in a little bit later after we started. I'm moving the exam from Friday. So we won't have an exam this week. It's gonna be Wednesday of next week. All right. So jot that down somewhere in your notes, or put it on your calendar. That because normally we take an exam every 2 weeks, but the fact that we missed Friday and Monday, but we did have class Monday night, but it wasn't that many people, so I can't count that as a class, even though I put the video up on Blackboard. I mean on YouTube. Yeah, so we'll stop here, and then we're gonna pick this up on Friday. We're gonna finish this example, and then we're gonna do the other ones.
Okay, have a great day.
All right, thank you. Y'all have a good day. Let's see, double, triple, 2, 2, 3. We like. I need to look that up.